Imagine programming an autonomous agent, right? Like giving it this incredibly strict set of mission-critical objectives and then just intentionally dropping it into a completely broken, glitching environment.
Just to see if it survives.
Exactly.
Yeah.
Just to see what it does. And we are talking about, testing a clean REST API here.
Oh, definitely not. Where a payload just returns a 200 OK or it doesn't.
Right, that's too easy.
Hmm.
Today, we're doing a deep dive into a framework that treats modern web browsers not as, software to be tested, but as hostile, unpredictable territory.
Which, let's be honest, is the actual reality of modern front-end architectures.
Oh, 100%.
We all pretend that our single-page applications are perfectly deterministic. We pretend that when Reactor View updates the virtual DOM, the real browser DOM perfectly mirrors that state in the exact millisecond we expect.
Right, in a perfect world.
But anyone who has spent, more than an hour writing end-to-end tests knows that is a complete fiction. It just doesn't happen.
Yeah, the synchronization issues alone are an absolute nightmare. I mean, you have hydration mismatches, you have CSS transitions that block the main thread.
This is long enough to cause a timeout, right?
Exactly. Or you have third-party iframes just hijacking the stacking context out of nowhere. The environment is inherently hostile to automation.
It's actively fighting back.
It really is.
Yeah.
And that is exactly what makes today's sources so compelling. We've got a fascinating stack today for you, looking at a system called the Feral Architect.
Great name, by the way.
Such a good name. We're looking at highly technical developer files, code-base excerpts, and these wild theoretical architecture documents. And the mission of this deep dive is to explore how this system redefines automated software testing.
Right, not just as a series of code scripts.
Yeah, but as this rigid framework of physical agency and structural fail-safes. And I want to assure you listening right now, you really don't need to be a software engineer to be captivated by this.
No, not at all.
Because the creator of this system, the architect, they aren't just approaching this as a coder. It reads like the work of a part-time stand-up philosopher.
That is highly accurate, actually. The architecture is steeped in this intensely philosophical worldview.
Yeah, it actively searches for the logical beauty in a failed state, which is just a wild concept.
It doesn't just want to know that the app broke. It is obsessed with the structural reality of why it broke and how the system can physically navigate around that breakage to continue its mission.
Okay, let's unpack this. Because before we can even look at how the system survives these catastrophic failures, we first have to establish the intense philosophical laws that govern its every move.
Right, the ground rules.
Yeah, we need to look at what the sources call the principal objective. The Feral Architect is built entirely around achieving 100% deterministic verification of UI flows through a zero-trust architecture.
And zero trust is a concept we usually reserve for cybersecurity. Right?
Yeah, exactly.
Like the idea that you never trust the network. You authenticate every single packet. Well, here, the architect has mapped that exact philosophy directly onto the document object model, the DOM.
The system fundamentally assumes that the UI state never matches the code intent.
Never. It doesn't matter if the test script just executed a click command on a button perfectly. The system refuses to believe the application responded correctly.
Until it physically verifies the resulting DOM mutation. It's incredibly paranoid.
Deeply paranoid.
And to manage that paranoia, the architecture is governed by 17 foundational laws. Now, obviously, we don't have time to dissect all 17 today.
You'd be here all week.
Right. But the ones detailed in our stack are just fascinating. So let's start with what the documentation calls the Feral Grit mandate.
Oh, this is where that concept of physical agency really crystallizes.
It really does. It mandates asynchronous survival logic.
Right. So if the testing loop encounters a roadblock, say an expected modal hasn't appeared, or a button is obscured by some weird z-index layering issue.
Which happens all the time.
All the time. The agent is explicitly instructed not to crash. It is forced to improvise workarounds.
But hold on, let me push back on this right away.
Yeah.
I get the web UI is a chaotic, untrustworthy wilderness, and this AI is supposed to be this hardened survivalist navigating it. But mathematically and computationally, how do you program a machine to have grip?
Yeah, it sounds impossible, right?
Yeah. I mean, so software usually just executes or crashes. If you tell an LLM-backed agent to quote-unquote improvise a workaround as a playwright environment, Aren't you just begging for infinite loops?
Oh, absolutely.
It tries clicking slightly to the left, it fails, and suddenly your CI pipeline minutes are just burning into the sun.
That is the exact risk of injecting probabilistic models into deterministic testing. And it is exactly why the feral grit mandate is permanently coupled with the Vulkan emulation rule.
Ah, right, absolute objectivity.
Exactly. The mandate is to survive, but the rule is to report without bias.
So if we connect this to the bigger picture,
Right. If we connect this to the bigger picture, the architect's philosophy is rooted in acknowledging chaos. What's fascinating here is how they balance these two forces.
the grit and the logic.
Yeah. The feral grit mandate gives the agent the asynchronous freedom to pull the DOM, to wait for network idle states, to perhaps attempt an alternative navigation path if a direct URL routing fails.
Just trying to stay alive.
But the Vulkan emulation rule restricts the evaluation of that survival. The system must report its findings purely on expected versus actual behavior.
So it can't make excuses for the app.
No, not at all. It cannot say, well, the submit button was hidden, but I found a way to submit via a weird keyboard shortcut, so technically the test passes.
Wow.
No. The test failed structurally, even if the agent survived functionally.
So it's separating the agent's ability to navigate the wreckage from the actual health of the application. Like, it survives the crash so it can pull the flight recorder, not so it can pretend the plane didn't crash.
Precisely. And this ties directly into the O-ring rule.
Right, the O-ring rule.
Yeah.
Which is obviously a reference to the Challenger disaster.
A very grim but accurate reference, yeah.
The mandate to always identify the structural root cause of a failure, rather than just accepting surface-level errors.
Because surface-level errors in modern web frameworks are notorious liars. I mean, you get a generic React minified error or a playwright timeout or error locator .click.
Which tells you absolutely nothing about the state of the system.
Nothing. The O-ring rule forces the architecture to dig deeper, like was the button detached from the DOM during a rapid re-render?
Or was there an unhandled promise rejection in the background that silently killed the state machine?
Exactly. And the documentation goes even further with something called the bad code purge.
Right. I loved reading about this. It actively rejects what it calls corrupted legacy variables.
It forces tests to execute perfect state resets. It refuses to let test data bleed over from one context to the next.
So the coder philosopher here refuses to trust the environment entirely, demanding verification of reality at every single turn.
The environment is compromised, the app's internal logic is suspect, and the only truth we have is what we can physically verify in the DOM at this exact millisecond. That's the baseline.
But this introduces a massive contradiction, doesn't it?
Oh, yeah.
Like, we've built this incredibly paranoid system. It doesn't trust the DOM. It doesn't trust the network. It requires absolute zero trust verification.
Right.
But to navigate this hostile environment, the feral architect relies heavily on generative AI.
Oh, the irony.
Right. It is using an LLM to interpret the UI state and write the playwright test assertions on the fly. And generative AI is notoriously the most untrustworthy hallucination-prone technology in our current stack.
By far.
So how do you make a deeply paranoid system trust a probabilistic hallucination engine?
Well, you don't. You put the intelligence in a structural straitjacket.
I love that phrasing, a structural straitjacket. Which brings us right to the restraint mechanisms.
The golden schematic.
Yes. The system requires the AI to generate code, but it treats the AI's output with the same zero-trust paranoia it applies to the web browser. The sources detail how the system prevents generative AI from hallucinating non-existent commands using this golden template.
It acts as a rigid RG constraint retrieval augmented generation.
But it's different here, right?
Very different. Usually RG retrieves context about the application's features or data.
Yeah.
Here, they aren't retrieving context. They're retrieving the exact abstract syntax tree shape that the output must conform to.
A physical schematic.
Yes. The AI isn't asked to write a test. It is commanded to trace the specific, verified execution path.
And the structural laws enforcing this are just draconian. Like, let's look at what they call the law of the step.
Oh, this one is fascinating.
Every single action the AI generates must be strictly wrapped in a specific syntax. It has to track it with a wait test.step, followed by a string label, followed by an asynchronous callback containing the actual playwright locators.
And, why do you think that is? Like, why force the LLM to write so much boilerplate just for a simple click?
Well, from what I read, it's because Playwright's trace viewer relies on those test.step blocks to organize the timeline.
Exact.
Right, because if the LLM just spits out a flat list of await page.click and it fails, You just have a giant unreadable stack trace.
A completely useless blob of text.
Yeah, the test.step gives the system physical demarcations to point back to.
It forces the LLM to conceptually chunk its actions. But then, look at LO1 in the schematic, the helper function bypass.
Oh yeah, the AI is strictly forbidden from using that exact same test.step syntax if it extracts logic into a helper function.
It is only allowed to use raw commands there.
Which feels super contradictory at first, like you just commanded it to use test.step for everything.
Right, but wait. Think about what happens if you nest a test.step inside another test.step.
Oh, and you don't handle the promise resolution perfectly.
Exactly. Playwright's execution context can leak or completely deadlock.
Oh, well. And the architect knows that LLMs struggle with nested asynchronous contexts.
They're terrible at it. They are essentially probabilistic text predictors. They don't hold an actual cost stack in their memory.
Right, they're just guessing the next word.
So if you let them nest promise-based steps, they will eventually drop in a weight, create an unhandled rejection, and just silently kill the runner. The helper function bypass prevents the LLM from building an architecture that collapses under its own complexity.
That makes total sense.
Right.
But my absolute favorite piece of this paranoia, and it really is paranoia, is Law 2.
The brackets.
The system's obsession with brackets and parentheses. The prompt injected into the AI literally says, quote, "Pay attention to your parentheses and if statements. Do not drop the closing brace."
It's just so funny to read.
It is hilarious. I mean, it's called the feral architect, implying this wild, untamed beast, but it's bound by the most obsessive-compulsive formatting rules ever. It's being micromanaged on basic TypeScript syntax, like a junior dev on their first pull request.
Well, this raises an important question, though. Why does an advanced multimodal model capable of analyzing complex UI layouts need to be reminded about basic punctuation?
It seems ridiculous, yeah.
But it goes back to the token prediction mechanics. When an LLM generates a long, complex string of TypeScript, especially when it's reasoning about locators and assertions simultaneously, the probability distribution for the closing brace drops as the distance from the opening brace increases.
It literally forgets it opened a block.
It just forgets. True freedom requires boundaries.
And the architect uses what the codebase refers to as the Reverend Silvertone protocol to enforce those boundaries, which is just, what a name.
This is theatrical.
It really is. The system speaks to the AI with these quasi-religious commandments. It tells the agent, you are operating under strict syntax laws. Your probabilistic memory is flawed and prone to syntax errors. You will trace the physical schematic exactly.
It's psychological engineering essentially applied to a latent space.
Wow.
By forcing the LLM to acknowledge its own probabilistic flaws right in the system prompt, it heavily biases the generation toward conservative, syntactically rigid outputs.
But even after all that psychological engineering, the feral architect still doesn't trust the output.
Of course not.
The AI generates the script, but before it ever touches the execution environment, the system subjects it to what the documentation calls the brute force solder.
The deployment and solder phase. The code is scrubbed.
Right, and I want to challenge the methodology here a bit because the sources say the system uses a regular expression, the quote-unquote comma immune addition, to scrub the LLM output.
Yeah, regex parsing code.
It strips out conversational markdown, forces correct indentation, and specifically targets trailing commas around the test.step callbacks, soldering them into the exact required TypeScript format.
That's aggressive.
But regex parsing an LLM's code output feels incredibly brittle. I mean, if the LLM hallucinated a slightly different code block structure, the regex wouldn't just fail. It could potentially mangle the abstract syntax tree entirely.
Oh, absolutely. It could turn it into garbage.
So why not just use an AST parser like Babel or TypeScript's compiler API to properly format the code?
That is a phenomenal point, and it speaks directly to the constraints of the environment.
Piece of the speed.
Exactly. Loading a full AST parser and running a compilation pass on every single dynamically generated test script inside the CI pipeline introduces massive latency and dependency overhead.
Oh, right. You're doing this on the fly.
The brute force solder is exactly that, brute force. It is a lightweight, low-level string manipulation designed for raw, unadulterated speed. Yes, it is brittle, but that brittleness is mitigated by the rigid RAG constraint we just discussed.
Because it's already in the schematic.
Right. The regex only works because the LLM is already in a straitjacket.
It's like an assembly line. The LLM extrudes the raw material, and the regex acts as the physical die that stamps it into the final shape.
That's a perfect analogy.
And once it's stamped, the system takes this newly generated soldered script and physically anchors it into a quarantine folder.
Yes, the zero trust guardrails. It doesn't allow the feral script to live alongside the human written
It
tests.
slaps a tag on it, an add quarantine tag,
It ensures the script is physically air-gapped from the core architecture.
and the paranoia continues. It hard maps the exact path to the sensitive vault, the .env.local file. If the system cannot find the Gemini API key, it halts immediately.
No graceful degradation.
None. Physical air gap enforcement. Pull the plug immediately.
And it goes even further than that. It automatically appends a / at TS no check directive to the top of every single generated feral file.
Now, okay, as someone who appreciates type safety, reading that physically hurt me.
It's controversial for sure.
You are intentionally injecting raw, untype-checked TypeScript into the repository.
Because the compilation failure of the master branch is just unacceptable.
Ah, so it protects the global build.
Right. The architect recognizes that the feral agent might generate a script that technically functions in Playwright, but maybe it uses an implicit any type or a non-null assertion that violates the repository's strict sconfig.
And if you let the TypeScript compiler evaluate that feral code alongside the human code,
A hallucinated type definition could fail the entire global build. So by injecting the tsend nocheck directive, the system isolates the blast radius, so feral code never breaks the global build.
it's just layer upon layer of failsafes. The intelligence is bounded by the Reverend Silvertongue prompt, soldered into shape by regex, quarantined in a specific folder, and stripped of type checking authority.
It is completely locked in a box.
But eventually you have to open the box.
Right.
Right. Now that the feral AI is strictly coded and soldered into place, what happens when it tries to run and the outside world fights back?
The script has to leave the sterile quarantine and actually interact with the physical application.
And the external network. And here's where it gets really interesting, because when it runs, the execution phase begins. The runner translates these markdown QA tasks, these perfectly soldered scripts, and executes them against the modern web API environment.
And modern API environments are notoriously difficult.
Which is an understatement. Because these tests require constant communication with the multimodal AI to evaluate the UI state. Which means you are dealing with API rate limits.
Network topologies are unforgiving. You're going to get throttled.
The sources detail an entire operational resilience layer dedicated to this exact problem, called the throttle protocol.
This is one of the most brilliant parts of the system.
It really is. The system is specifically designed to intercept the dreaded HTTP 429 status code, the too many requests error.
And I love what the code base refers to the 429 error as.
The API bouncer.
The API bouncer.
Which is such a visceral way to describe network throttling. And the way the throttle protocol handles this bouncer is so clever.
It utilizes an exponential backoff strategy, right?
Exactly. Managed by a retry wrapper. So when the test hits that 429 error, it doesn't just crash and fail the test.
Like most automated tests would.
Right, they just shatter. But this system catches the exception, forces a hard 20-second cooldown, and essentially steps back from the server door.
It waits outside the club.
It literally waits outside the club until the API bouncer looks away, checks its pulse, and tries to get back in. It will do this up to 3 times before fully locking down.
What's fascinating here is the underlying economics driving this specific protocol. Because the sources mention something called the feral workaround.
Right. The architect is deliberately utilizing the free tier Gemini 2.5 Flash model as a workaround to bypass paywalls, making this throttle protocol essential for survival.
But I'm sure you have thoughts on this architecture choice.
Oh, I totally do. Let me push back on this architecture, because if you are building this highly sophisticated deterministic zero-trust testing framework, why are you cheaping out on the API?
It seems counterintuitive.
Very. Why build an entire throttle protocol, complete with asynchronous wait states and retry wrappers, just to game a free tier? Why not just pay for a premium enterprise tier with dedicated throughput and bypass the bouncer entirely?
Because paying for dedicated throughput is an illusion of control.
Wait, really? How so?
Well, even on premium enterprise tiers, if you spin up parallel CI workers running hundreds of tests simultaneously, you will eventually hit token bucket limits or concurrency caps.
Oh, that makes sense.
The API bouncer always exists, he just checks different VIP lists.
Oh, wow. That is a great point.
And the philosopher architect isn't just trying to save money here. By forcing the system to operate on the constrained free tier during development, they're essentially practicing chaos engineering.
Building resilience into the DNA.
Exactly. This is true operational resilience. Most automated tests are brittle and fail at the slightest network hiccup. This system has asynchronous cooldowns built directly into its operational cycle. The throttle protocol forces the test runner to respect the environment's limitations rather than trying to brute force through them with dollars.
It respects the environment. It makes the agent inherently patient. Most test automation assumes immediate availability, but the feral architect assumes hostility and unavailability.
It waits.
And when the bouncer finally looks away, it slips back in and resumes the playwright trace exactly where it left off. I am absolutely blown away by the resilience here.
It's emulating human latency. A human tester wouldn't throw their laptop out the window if an API request failed.
No, they just hit refresh.
Exactly.
Okay, so the system has survived the bouncer. The throttle protocol worked. It's inside the application, executing its quarantine code. But then it encounters the inevitable, a true structural failure inside the application's UI.
It was bound to happen.
The checkout button is gone. The modal is broken. The server returned to 500.
Yeah.
Does the feral agent finally give up and die?
No. That is the exact moment it transitions from being a survivor to being a detective.
And this brings us to the absolute core of the deep dive. Section 4, the art of the fail. We really need to look closely at the playwright configuration outlined in the sources.
The physical environment is highly standardized. Standard port 5173, a strict 30-second global timeout.
And the persistence logic is really contextual. It allows 2 retries if it detects it is running in a continuous integration environment.
The automated server pipelines.
Right. But it only allows 1 retry if it is running locally on a developer's machine.
Because developers don't want to wait for their local runner to fail 3 times in a row, but CI pipelines need maximum resilience against network flakes.
Exactly. But the true genius here is in the artifact retention policy. The system is built to retain traces, videos, and screenshots, specifically on failure.
If the test passes, the data is just dumped into the void. Archiving success is a waste of disk space.
Nobody cares if it passed. But if it fails, it triggers what the architect calls the sentinel catch.
This is incredible.
It really is. When a structural failure hits, the framework doesn't just log a stack trace. Like an airplane crash investigator, it captures its own black box data.
Securing the crash site.
Yes, the raw standard output, the standard error bytes, the DOM snapshot, and crucial visual screenshots of the exact millisecond of failure.
It preserves the analog glitch, the immediate physical reality of the application at the moment of death.
And then it takes that black box data and initiates negative space debugging. This just blew my mind when I read it.
It's a game changer.
The system doesn't just pass the text logs back to the LLM. It takes the high-resolution screenshot of the failure, converts the entire image into base 64 encoded data.
Turning the visual pixels into a massive string of text.
Yes, and injects it alongside the logs for a multimodal analysis.
But wait, let's look at the payload mechanics of that. Base 64 encoding a full-screen playwright screenshot creates a massive token payload. We are talking hundreds of thousands of characters being pushed through the API on every single failure.
That's huge.
The latency on that multimodal request has to be significant. Is the juice really worth the squeeze just to look at a screenshot?
I wondered the same thing. But it is entirely worth the squeeze when you consider how it analyzes that screenshot. The prompt doesn't just ask the AI, why didn't the button click? The sources specifically detail the command, identify any overlays, loading states, or rendering glitches. They call it negative space debugging.
Right, negative space debugging. It explicitly forces the attention mechanism of the multimodal model to look away from the focal point of the failure.
Because the focal point is almost always a symptom, not the disease.
Think about how human developers debug UI failures. The console logs scream, error, element with ID submit checkout is not interactable. So the developer spends 2 hours staring at the React component for the checkout button.
Checking the state, checking the disabled props.
Completely hyper-focused on the button itself.
When in reality, a transparent CSS overlay from a broken analytics script was stretched across the entire viewport, intercepting all the pointer events.
The button was fine. The negative space around the button was toxic.
Exactly. This system steps back. It evaluates the z-index stacking. It looks for opacity shifts. It analyzes the visual periphery.
This raises an important question, though. How often do we misdiagnose our own failures by hyper-focusing on the immediate obstacle? The philosopher-architect finds incredible value and literal data points in the negative space of a failed state. The absence of expected behavior is intrinsically tied to the presence of unexpected context.
It's like trying to open a locked door, failing. But instead of just logging door locked, the system steps back, looks at the whole room, and notes that a massive bookshelf has fallen across the hallway.
It is profound diagnostic clarity.
It really is. I'm in awe of this negative space hack. So the AI processes the multimodal payload. It correlates the playwright timeout log with the visual evidence of the collapsed structural beam. It understands the root cause.
But now what? The framework has to translate this feral investigation into something the human developers can actually use.
Right. It has to generate an artifact. And this is the final phase we see in the sources. The generation of April-approved reports and the execution of the ultimate failsafe. The feral agent is tasked with turning that complex black box failure data into a comprehensive bug report.
Using a rigid markdown template, it cannot just dump a paragraph of AI thoughts.
No, the template enforces strict sections. Actual behavior, expected behavior,
Right.
acceptance criteria.
It must provide physical artifacts, direct file paths to the retained screenshots, and trace zip files.
So the human doesn't just have to take the AI's word for it. But the defining characteristic of this report is the impact section.
Yes.
So what does this all mean? Why mandate an impact section for an automated QA script? The sources explicitly state that the AI must describe how the bug blocks the human OS.
The human operating system.
It forces the feral agent to translate DOM manipulation errors into human usability blockers.
It is programmed human empathy.
It is. And it ties into a concept the architect calls the reverse aposematism defense.
Which is such a cool biological metaphor.
Right. In evolutionary biology, aposematism is when a toxic animal uses bright warning colors, like a poison dart frog to signal, "Stay away, I am dangerous to consume." The feral architect uses reverse aposematism.
It actively curates its output to be non-toxic.
Yes, it takes the deeply toxic, dense, impenetrable garble of a massive playwright stack trace, and it digests it. It formats the output to be impeccably safe for non-technical stakeholders to read.
The system treats human attention as a highly precious, easily depleted resource that shouldn't be wasted.
It demands an April-approved report. Now, the sources don't identify who April is, presumably a product manager, a QA lead, or some non-technical stakeholder, but the persona she represents is clear.
The standard is that the report must be so pristine and contextualized that April can read the markdown file and immediately understand the business impact of the failure.
Without ever looking at a line of code, knowledge is most valuable when understood and applied. The system ensures the analog glitch is perfectly communicated to humans.
Acting as the ultimate architect failsafe before code is merged.
But here is where the paranoia of the feral architect makes its final stand. We have to look at the ultimate failsafe, the syntax fault.
Because what happens if the AI API itself drops the connection during the report generation phase?
Exactly. The system caught the error, the Sentinel captured the black box data, it sent the base64 screenshot to the LLM, and then the connection just dies.
Network timeout.
The LLM goes down, the analysis halts. Does the failure just evaporate into the void because the AI couldn't write the beautifully formatted April-approved markdown?
Not a chance. The system has a fallback.
It falls back to a hard-coded try-catch block surrounding the AI generation phase. If the multimodal API drops, the system catches the connection error. And instead of failing gracefully, it executes a syntax fault protocol.
It writes the file anyway.
It bypasses the AI completely and automatically writes a syntax fault report directly to the local bug reports directory.
It generates a fallback header stating that the API dropped the connection, but structural failure was still caught.
And then it takes the raw, unformatted black box log and physically injects it into the markdown file.
So it sacrifices the reverse aposematism defense in order to preserve the O-ring rule.
Yes. It knows the raw log is toxic to read, but it guarantees that some physical record of the failure survives to reach the human CI pipeline, so no structural failure ever goes undocumented.
It ensures that a structurally broken application is never silently merged into the master branch just because the diagnostic tool had a random network hiccup. It is absolute relentless defensive engineering.
A system designed to expect betrayal at every single layer.
The DOM will lie, the API will throttle, the LLM will hallucinate, the network will drop.
And yet the architecture is specifically built to absorb all of those betrayals and still deliver a deterministic truth about the state of the application.
It's remarkable.
It really makes you evaluate the systems you interact with daily. Think about the architecture of your own professional workflows. How often do you face an environment that doesn't behave the way you expect? Are your automated processes brittle? Do they shatter at the first sign of an API bouncer?
Or do you have your own feral grit mandate? Do you build asynchronous survival logic into your projects, anticipating the failure and planning the workaround before the crash ever happens?
And when you do encounter a failure in your personal or professional life, how often do you utilize negative space debugging?
It is so easy to hyper-focus on the immediate console error, the immediate blocker right in front of your face.
But how often do we step back, look at the visual periphery of our projects, the context, and realize the real problem is a structural dependency blocking the hallway?
Which leaves us with a final, somewhat provocative thought to mull over. The entire premise of this deep dive was analyzing an architecture that independently investigates its environment, visually analyzes the negative space of its own failures, patiently waits out rate limit bouncers, and beautifully documents its findings with profound empathy for the human OS.
It's doing our jobs better than we do.
Right. So if we are now capable of building architectures that are this resilient systems that possess this level of operational resilience and autonomous diagnostic clarity, at what point does the human QA architect become entirely obsolete?
Well,
If the system can perfectly articulate the analog glitch and perfectly translate the structural failure into human-readable impact, are we approaching a horizon where only the feral intelligence is left, continuously and silently evolving the digital world in the dark long after we have stopped watching the logs?
an agent built to expect a broken world, eventually realizing it doesn't need us to fix it. The feral architect doesn't just navigate the chaotic wilderness of the modern web. It has learned to map it, survive it, and document its wreckage with terrifying precision. Until next time, keep diving deep.